Once again, hello everyone. We welcome here our next speaker. This is Iván Mихайлин. He will tell some information about his course, which is called Sequential Data, Representation and Analysis. Ivan is a graduate student at the University of California in San Diego. And today he joined us to tell a little bit more about what you're going to discuss throughout your studies. The main goal of his course is to introduce students to new methods of sequence analysis and help them develop the skills to use these methods in practice. I'm sure that this will be as informative as the previous presentation, so let's briefly, yes, listen to our speaker. You're welcome.
Well, hello there. So yes, my name is Ivan, and I'm a graduate student. My main interest is complexity theory, algorithmic theory, arithmetic theory. So theory with some prefix before it. So you can tell my research interests are just a little bit too exotic for general public. So I don't want to, scare everyone with telling about my projects. So let me just dig in and tell you what we're actually going to study in the class. I had a blast recording for you. So it's about sequences and how to analyze and represent them. So that's you can get from the name, right? There are two different topics that are composing into two different blocks. The first block is about the data that comes from biology, mostly. It's about how to look for substrings or how to combine strings from pieces, which is basically the task that comes from genomics. Generally, you have when you're extracting a genome, you have your pieces that are cut from basically a random location and then are given to you like in a bag. So think of that, like you have this a newspaper from Korea and you don't speak Korean, and it was cut through a schroeder, and now you assign a task to piece it back together without knowing Korean or where those pieces are coming from, just by well, those letters look similar, so let's put them together. So something like that looks impossible, but surprisingly we can do that by being clever. That's what we really like to do, is just be clever and think your way through this. And the main idea from this section that I really want to I'm really investing into putting this idea into your head, like as deep as I can, that it really matters how to represent your data, because depending on what method of representation you would use, you will get completely different results. Usually when you're looking at strings, they're just some letters and you cannot do much with them. So people start doing different things with them, like, hey, how about we'll build a suffix tree, which when you first look at it is an insane idea, but then you can do just magic with it. You can look for substrings in a text in time proportional to the pattern you're looking for. So like, imagine you have a book and you want to look up a specific phrase in that book. So if you just think of it for a few minutes, it seems that the best you can do is just scan through the book page by page and look for the phrase, which is really time consuming, right? But for some, mostly with like blood magic, you can rearrange your book in this like insanity called suffix tree, and then you can actually just like look for any particular phrase in that book like this, just in a second, which again just comes from being really clever about how how to represent your data. So there would be a few other examples. For example, with bioinformatics, there was a great breakthrough when people stopped thinking about words as again just bunch of letters on a paper. Well, in this case, like we have this genome, so we have a bunch of genes, right? And we just look at them, and then there is not much we can do, and start think of them as a graph with some underlying properties, and then surprisingly we can do all this. We can start actually assembling genomes in reasonable time with reasonable accuracy. So yes, so the first half of the class would be all about how to represent your data, how to choose your representation, how do some tricks and be surprisingly just insanely efficient with doing stuff to your data. And the second part of the class, so there is this big word, the big data, and no one really knows what it is. Everyone is promising they're doing it, but it's in a very naive sense. It just means that you don't have enough resources to store your data, to analyze your data as a whole. So you need to process it piece by piece, right? So basically, like you imagine you are assigned to watch TV for a week, right? So you cannot memorize every single thing that comes from the TV. So your brain somehow gets the important stuff. It gets the highlights, it gets the patterns, it gets some recurring themes, it gets the theme songs of some movies that are just stuck into your head forever. So we need to make computer be able to do the same. We need to make computers smart enough to not just greedily look through the data as if it belongs to them, right? So it's called, it's not a section called big data, because that would be a little misleading. It's called the streaming algorithm section, right? So you have your data that comes as a stream, and you can just like watch it as it flies by. And that is a lot what is happening. For example, if you're a server, well, if you have a server that is looking at the internet traffic, you don't have the memory to store every single thing that's passing through you, but you still want to be, to understand what's going on. Maybe you want to see if there are some activities that are unlawful, for example. So to do that, you need to find unlawful, something that isn't right, you need to understand what's right. So you need a sense of what's happening. So basically, it's the whole thing about getting a sense of what is happening from just watching the data. And the main idea from this one is that it's very, very important to know where is your data coming from. A lot of things that you can do with actual real world stuff, you cannot do with just a sequence of random data points. It's absurd. It has no patterns. It has nothing, none of the useful information. So to look for patterns, you usually need to know what you're looking for, right? So for example, if you're looking at sounds, that is very useful, because now you can do stuff. You can forget about actual if your data points are the volumes, right, and the frequency of the sound, then volume is basically irrelevant. To analyze the speech, you only need the frequencies. So you extract the frequencies, and then you can discard noise, and you can go to this Fourier domain and just look at the few major sequences at every single time and actually extract the text that you think is the speech. So this is a speech recognition. To do that on the fly, you cannot recognize a speech from the white noise. So it is important for you to know ahead that what you're listening to is human speech, right? That is a straightforward idea, but it is surprisingly easy to forget that you need to study what exactly you're planning to use your algorithms for. You cannot just learn algorithms and then pick, the one with the best performance any time and just use it because the book says or the internet says it's the right one. You need to get like this close relations with your data. You need to understand what's going on. Maybe you need to find, or maybe your data has like some nice linear representation, and then you use your linear sketches. You cannot know to use linear sketches just because they're good, just because they're hype. You need to actually know that your data is valid for this particular method. And so this second part is about choosing the right method, not to represent your data, but just how to learn stuff about your data. But before that, you need to actually know what to look for. So know your data. So 2 blocks, 2 different ideas. They kind of combine sometimes. So yeah, hopefully from this class, by the end of it, first of all, you would hear a lot of me talking. That's not, I apologize in advance. I heard my own speech. It's horrible, you know that. Just, yeah, I don't know how people listen to me. But on the other hand, I hopefully you would be up to speed with modern approaches to genome analysis, right? It wouldn't be, I'm not giving specific details of a modern assemblers, but I am giving you the ideas for the approach that is used for in current modern assemblers. So if you want to go and study genomics, take this class, learn stuff, and then go ahead and explore. Same with big data. I will not give you specifics about how to analyze your data, but I'll give you all the ideas and all the methods that are currently used in like, exploring statistics of the data, basic machine learning on the data, like how to represent your data with decision trees, or how to cluster your data. There are roughly a billion different methods to do that, but there are some underlying themes that you will pick up from this class, and then you can actually go learn the one particular methods and use them. So hopefully you will be at the level where you can study on your own in any particular topic about sequence analysis as you want. So this is your ground level, and from here you can go wherever direction you want. Yeah, so that's what I'll be talking about for a lot of lectures in 15 minutes. And any questions, please?
Yes, thank you a lot for your presentation. It was quite detailed. And I know that a lot of students even now ask about your course because it's quite interesting, and it can give a really great start for their further development, as you've mentioned yourself. Now we have a couple of questions here. The first one, can you give an example of an exotic or unusual but useful way to represent data?
Oh yeah, that's a good question. So I have my favorite one because I was working on it for quite some time. So there is this like superstring problem that's related to genome assembly, and there is a thing called a hierarchical graph. So basically, what you do, you start with your string, and you represent it as a path from 0 string through all its suffixes and through all its prefixes, like just a pair of passes, which looks like wasteful and weird, and just it came up basically by accident. But then what happens is that if your string is weird, or just if it's hard to deal with, for this particular type of algorithm, this nice loop will turn into braid or a knot, and study the geometry of it. It's actually a lot clearer. That just the picture you can get from it is a lot clearer for you and for the computer to understand what's so bad about this particular string. And then when you put like several strings together, you get this like entangled, weirdest thing ever. And the underlying geometry is actually incredibly useful. So basically, by representing your strings as a pair of like wires, which makes no sense when you see it first time, is just really, really useful, and I find that fascinating.
Yes, thank you. Now the next question: what practical application will be used in this course?
So again, there would be two main things. The first part we will be concerned about genomics, right? So the main task would be you will be given some data that is biologically inspired, and you will basically need to do a genome assembly task. So you will need to build your very, very simple genome assembler. It will not deal with all the messy stuff that comes from the actual real world thing, but it will do the main thing, like what would be assembler like if we lived in a perfect world. And then if you like, from there you can actually go and study how people build on that to deal with the actual mess that is a real world DNA. And the second one is mostly about just getting some basic information about your data stream. Again, the main application is a server or a router. So just taking some ideas from this like big data analysis and applying it to this like rather small category, but all the methods can be used in the actual big data analysis. So this is like a toy example, but I really believe that it gives you the skills to actually go into the real world and try to apply them.
Yeah, it was a very great example. Thank you. And the last question that I see here: how can we use data mining for better marketing? And do you think it exists in Russian market?
Well, I'm not particularly the right person to answer at least the second part of it. Again, I am a modest theoretician. I don't deal with real world mostly in my studies, but I would assume yes. Like there is no like data mining, of course, exists in marketing. That's, I think, one of the three things that comes to mind if you think of an application to marketing. There are weirder things people do, like I know about people who mine your location through Tinder to give you targeted ads. So yeah, so be careful about that. Yeah, but this class wouldn't be particularly about data mining. It's as the name suggests, it's actually about like sequence analysis. It's not particularly machine learning oriented. There would be some examples in machine, like how to implement machine learning on sequences. Like we'll have these like basic machine learning computations on on data streams, but it's mostly about actual algorithms, about actual programming. So if you're interested about like using already existing software to do data mining, that this class will be still great for you, but not enhancing this particular skill.
Thank you. I think you did a very great summary, a sum up maybe of your course. And as I can see, there are no questions left. So thank you once again for your time, for your presentation. And I wish you a good day. Thank you. As for our listeners, I remind that we have some lectures left. So stay tuned and please monitor our official website for the links. See you soon.
Bye.
Goodbye.